Okay, we'd like to talk about the intensity of a sound, and if we're talking about intensity, um, then another word for that might be loudness, or volume, loudness, how loud something is, and really the equation for intensity is the power of a sound through an area. How much power of a sound is through an area. And you might remember that the units for power is watts. So we're talking about watts per, and the area is square meters. So watts per meter squared would be a unit for the intensity of a sound. So there's a couple different intensities of different sounds that we have. We have what's called the threshold of hearing. This is I of naught, or I zero, and the threshold of hearing is basically the lowest intensity sound in watts per square meter that a person could hear, and that is 1.0 times 10 to the minus 12 watts per square meter. 1 times 10 to the minus 12 watts per square meter. Usually we give the units for what we call absolute. These are absolute intensities. We're going to do something called relative intensities in the next video. But these are just absolute intensities of sound in watts per square meter. And this right here is called the threshold of hearing. Basically the lowest amount of power per square meter that you could possibly hear. Now, sometimes we use these units, but sometimes we use watts per square centimeter. So what would the threshold of hearing be in watts per square centimeter? And you might want to memorize both of these, because for the next video, sometimes we use either one of them. So if you want to convert, if you remember how to do that, 1 e negative 12 watts per square meter. We use our dimensional analysis here. 1 square meter. In a meter, there are 100 centimeters. So in 1 meter squared, there'd be 100 squared centimeters squared, if you remember how to do that. So we're going to divide this by 100, which would take it down to 1 e minus 14, but then we're going to divide it by 100 again, so we would get 1.0 times 10 to the minus 16 watts per centimeter squared. You might have tried to do this in your head and just thought it went down to minus 14 because we're dividing by 100, but this is area, so we're going to divide by 100 twice. So we can use either one of these as threshold of hearing, depending on what units we're going to use. There's also something called the threshold of pain, which I always thought would be a cool name for a band, the threshold of pain. And the threshold of pain is 1.0 E1 watts per square meter. You might realize that that's 10 watts per square meter. So we go from the threshold of hearing, which is 1 times 10 to the minus 12 watts per square meter, all the way up to 1 times 10 to the first, or 10 watts per square meter, at which point actual pain can be caused in the human ear when we get up to something that's this loud, and it's too much power coming through the square meter or the square centimeter in your ear drum, and could actually cause damage to your ear. So we have an upper level called the threshold of pain. We can obviously go up more than that, but severe damage would be caused. And then we have a lower level, a lower limit called the threshold of hearing at 1 times 10 to the minus 12 watts per square meter. Okay, so we're going to talk more about relative intensities later. This is absolute intensities. But what I want to look at is, how does the intensity of a sound change as you are further and further away from the source? So if you look at this drawing here, let's say we have someone claps their hand, they make a sound right here, and it's a certain amount of power per square meter. And let's say this goes out to, out here's a circle. It goes out through a circle. And the area of this isn't a circle, this is a sphere. The area of a sphere is 4 pi r squared. But I could go out bigger and bigger circles here. And they all include the 4 pi. So what I'm going to do is this is just a constant number, and they would all include the 4 pi. So I'm just going to pretend it's not there and just talk about the area that the power. So it's going to be a certain amount of power that's put out here, and that power is going to travel outwards, radially outwards through the spheres. And what kind of area does it go through? Because the intensity is power over area. So I'm going to keep the power exactly the same. I mean, it makes one kind of power at the beginning, and that power is going throughout, basically expanding areas. So the intensity is going to get less the further you are away from something. I think that might be common sense. The further you are away from something, the less intense, or the sound will be softer the further you are away. But I want to know, how does it change as you get further away? So let's just say that we had a certain power. Let's just make a nice easy number. Let's say it's 100 watts. 100 watts of power. So once it gets 1 meter away, the power comes 1 meter away, it crosses an area of this circle, which would be 4 pi r squared, but we're going to just forget about the 4 pi every time. It would go through an area of r squared. Well, this is, sorry, this is 1 meter away. So it would be 100 over 1 squared, which would be 100 watts per square meter. And so right here it'd be 100 would be my intensity. So as it comes out here and gets further away, now it's going through another area of a circle, and this would also be 4 pi r squared, but we're just ignoring the 4 pi. So this would be going through an area of r squared, which is 2 meters away. So it would be 100 divided by, the power is 100 still, but it'd be divided in the area, which would be 2 squared, which would be 4. So 100 divided by 4 would be 25. That would be my intensity, would be 25. So you'll see what happened here is we went twice as far away as we were here. And our intensity of the sound went down divided by 4. We went twice as far away, it went down divided by 4. So what happens if we get even further away? And so we come out to a really big circle, and the area of this, of course, would be 4 pi r squared, but we're ignoring the 4 pi. So the area would be r squared, which would be 1, 2, 3 radiuses. So 3 squared would be 9, and we take 100. The power is still 100, but in this time we would divide it by 9. So we would end up with like 11 would be our intensity. Okay? So what happens? We went 3 times farther away. Here we were twice as far away here. Now here we're 3 times farther away from there. And what happened to our intensity? It was divided by 9. So what would happen if we went clear out here 4 times further away? Well, we'd have our power 100 divided by our area, which would be 4 squared, 16. So 100, we have 100 divided by 16, and we'd be like at 6.3 would be our intensity. So our intensity drops off pretty quickly, and it drops off by the square of the distance away from it. So whenever we were trying to find an intensity out here, we divided it by we took our power and we divided it by our area. So intensity is proportional to 1 over the distance squared out to it. This is called an inverse square law. So as you get further and further away your intensity is going to drop. So if you look at this relationship here, I mean, what would happen? We could ask a question. What would happen if you were 5 times further away from some point? Like, let's say that right here we knew the intensity was 100 watts per square meter. But let's say we went out here 5 times further away. What would be our intensity? Well, if you went 5 times further away, it'd be 1 over 5 squared. It would be 25. So it'd be, the intensity would be divided by 25. It would be 4 out here. So we're going to have 1/25 the amount of intensity. So I can take, this r squared times the I, and that'll be I, let's call it intensity 1 times r1 squared. And that'll equal 1. That'll be a constant, which means that will equal the intensity anywhere else times the distance out to that place squared also. And you might recognize this kind of equality. This had a lot to do with gravity, right? We had g d1 squared equals g2 d2 squared. This is the exact same relationship. It's called an inverse square law. And there's a lot of inverse square laws in physics. It's kind of interesting that there's so many inverse square laws in physics, that the further you get away from something, the less it goes, but it goes down by the square of the distance. So we have intensity IR squared equals intensity somewhere else times the distance out to that place squared also. So hopefully that helps you understand absolute intensity formula and how the intensity changes as you are further away from a source.